Lesson 11:1, cross-sections and space figures. A polyhedron is a space figure, or a three-dimensional figure, whose surfaces are all polygons. So examples are prisms and pyramids. Parts of a polyhedron are faces, edges, and vertices. So the faces are the polygons, so in this case the rectangles or the quadrilaterals. The edges would be all of these segments, so there's 4 on top, 4 lateral edges, and then 4 on the bottom base, and then there's vertices. And the vertices are just the points that are here. How many faces, edges, and vertices are in each figure? List them. So in this first shape, it looks like it is a square pyramid. So I'm going to assume this bottom is a square. It's probably a quadrilateral, but square prism. Otherwise, you would just call it a pyramid, excuse me. So for faces, edges, and vertices, what we can look at is 5 faces. We have the bottom and then 4 lateral faces. Edges would be these segments, so that's 1, 2, 3, 4, and then 4 on our base for 8. And the vertices would be these orange dots for 5. And now if I needed to list them, my faces would be the 4 triangles. Those are called the lateral area. So triangle HGF, HFE, HED, HCG, and then the quadrilateral on the bottom, GFED. And then the edges would be segments, HF, HE, HD, HG. And then you could do the edges that are on the base. And notice my notation, they are segments. And then the vertices are just the points, so then you can just list the letter. On the bottom shape, how many faces do we have? We have 5. If we get specific here, the base would be a triangle. So this is a triangular prism because that base is replicated. It's just not sitting the way you would picture a prism to be sitting. So for faces, edges, and vertices, we have 5 faces, 9 edges, because we have 3 on the bottom base, 3 on this other base, and then the 1, 2, 3 here. And then our vertices, again, we have 6. So 3 here, 3 there. So then our notation, we have 2 triangular faces and then 3 rectangular faces. And then our edges would be all those segments, and there should be 9 of them. And then our vertices are all those points. You don't have to have them all written down, just a few. Euler's formula. For any polyhedron, the sum of the number of faces and vertices is 2 more than the number of its edges. So faces plus vertices equals edges plus 2. So in this first example, what we need to do is set up our formula. So the number of faces is what we don't know. The number of vertices is 20. Edges is 30. And if we add 2 to that, we have to have a balance in our equation. So we get a sum of 32. So x plus 20 is 32, so that missing value has got to be 12. So that means that we would have 12 faces on this shape. We just can't see them all to count them. Verify Euler's formula for this polyhedron. So let's count them. I see this as a hexagonal prism, because the hexagon happens twice. So that means I have a bottom face, a top face, and then these lateral faces, there would be 6 of them. So 6 plus 2 for 8. The edges, I have 6 edges laterally, 6 edges on the top, 6 edges on the bottom, so 6 times 3 for 18. And then vertices, I have 6 on top, 6 on bottom for 12. You just have to make sure that you don't count anything twice. So we have to verify Euler's formula. So that's edges, that's faces plus vertices equals edges plus 2. So you don't have to have that part written down, but you do need to have the 8 plus 12 equals 18 plus 2. And then we can see that 20 is equivalent to 20. On the bottom problem, it says, how many edges does this polyhedron have, given that it has 20 faces and 12 vertices? So we're still using Euler's formula. So the number of faces is 20. The number of vertices is 12. How many edges would we have to have? 30. The next vocab word is a net. A net is a two-dimensional diagram that you can fold to form a three-dimensional figure. Think of unfolding a cereal box, and that is spelled wrong. So these are all nets. This would make a triangular prism, and this would make a hexagonal pyramid, and over here we'd have a cube. We'll skip the top example. It says, draw a net for the box of crackers shown, label all dimensions. So what I'm going to do first is just draw my bottom. So this shape in here is going to be my base, and then this would be a lateral side and a lateral side. And then my other two lateral sides should be congruent. And now it looks like I'm only missing my top. And I could put my top over here, I could put it over there, I could put it on this bottom, or I could put it up here. And then I need to put in my dimensions. So my base is 14 by 6, and my lateral edges are 20. And then I can fill in my other values. Draw the net for the box of crackers shown. Label the net with its dimensions. So again, I'm going to start with that base. And now I just need to add my triangles. So this is what I'm looking at. I'm going to count my faces just to make sure. So 1, 2, 3, 4, and the bottom would be 5. 1, 2, 3, 4, 5. So if I fold that together, it should match. And now I just need my labels. So my bottom is 7 by 4. And then these areas over here are going to be 10. So that would make these 10 also. And that would reflect up on the top. So the triangles are the bases, and then these rectangles would be the lateral area. The second question says, is there another net that exists? Well, if I slide some things around here, if I wanted to put this here and maybe put this over here, I'd have some problems because of the 7 and the 10. So what I'd have to do is move that bottom around a little bit. So what I'm going to do is just slide my base here, and then I just need to add another piece in to separate my two 10 dimensions. So that's another way that we could have drawn our net. Match each of the 3D figures with its net. One net does not match a figure shown. So the first picture is a hexagonal prism. So that would have to be this one. That's the only one that has hexagons on it. The second object is a triangular prism, and that matches with this. And the last one, I think our choices are here, but we need to decide how many faces it has. And I'm counting 3. So then I have 3 faces, and over here I have 5, and my bottom, my base is a triangle. So I'm going to be looking at this shape. So the front face, the back face, the side face, and the bottom, so that's not really 3, it's 3 lateral and 1 base, so that's going to be this shape right here. And then this would be the one that doesn't fit with the others. A cross section, the intersection of a solid and a plane. So what we're going to do is think of maybe slicing it with a knife or slicing it with a sheet of paper, and then we have to figure out what shape is formed with that cross section. So it says, describe each cross section. So if I cut through this triangular prism, I would end up touching here, here, and then at this piece that's already drawn in. So this cross section would be a triangle. Up on top, again, this is already shown, but the other part would be over there, and this would be an ellipse or an oval. You haven't probably learned the word ellipse yet, but you will in Algebra 2. And then down on the bottom, again, this edge is shown, that edge is shown, that edge is shown. So this is going to look like it's going to be a square because I noticed that this is parallel to that. So then those distances should all be the same. Here's an example of a cross section. So if I have a prism and I can cut it, that's what I would have. And then the cross section is a non-equilateral triangle that is showing. The next slide says, draw a cross section formed by a plane perpendicular to the base. So perpendicular to the base, so I'm going to go perpendicular to that. So that would be maybe something like this. Excuse me, what I meant to say is I'm going to cut it perpendicular like this so that you can kind of see my cross section. If I draw it perpendicular to the blue, then you can't really see my face. So this would be perpendicular to the base. So that would be a rectangle. On the bottom it says draw the described cross section. So we want a plane that cuts off a corner of the cube. So I would argue that we just did that right here. So we will need to demonstrate that. So if I cut off a corner, it would form a triangle. Secondly, we want a plane that is tilted and intersects the left and right faces of the cube. So this would be the right face, this is the left face. So maybe I want to draw something like this, because now it intersects the left and it intersects the right. So that would be some kind of rectangle. And then the last picture says a plane that contains the red edges of the cube. So I already have two of the red edges on, so then I'm just going to draw a diagonal in, and again that would be some kind of rectangle. The last thing we're going to talk about today is a solid of revolutions, and this is really something that you get heavy into in calculus. It says describe the solid of revolutions you get by revolving each region about the line. So what happens if we spin this rectangle on line L? So this red piece has to stay on line L, and then it's going to spin in a circular motion around that. So that means if I spun it 90 degrees, it would be coming out at us. If I spun 180, it would be down here like that. So then if I just add some dimension to that, this would form a cylinder. Going down. If I take this triangle and I spin it, remember this red side has to stay here, but this point will drop down here if I go 180 degrees. And if I keep constantly spinning it, I'm going to get a cone. On top, if I spin 180, I'm going to get a circle. But remember, this is a three-dimensional figure, so it turns into a sphere. And the last green circle, if I spin 180, I'm going to end up down here. But again, remember, it's continually spinning, so then I have to have some connectors in there. And it's going to spin on the back side too. So what would you describe that shape as? I'm going to call it a donut. This concludes my lesson on 11.1 for geometry.